Hello everyone, I'm Chen Weizheng from Tsinghua University, and I'm happy to introduce our work EditableNeRF, editing topologically varying neural radiance fields by key points. In this work, we aim to enable end users to easily edit dynamic scenes and even support topological changes. Our key idea is to use weighted key points to model these dynamics. The input of our method is an image sequence from a single camera, and our network is trained fully automatically to model the scene based on key points. For example, in this video, we can model this scene of knocking on each piano key using a key point on the harp. After the network training, users can edit the scene by easily dragging the key points to desired new positions. Further, users can also make a video of playing a piece of music and render it in lower views. This can be done by simply dragging the key point and even slide on the piano keys, which is unseen in the training sequence. Neural radiance fields, also NeRF, is a method using an MLP as an implicit function to model a static scene as fields of density and color. Recent works have extended NeRF to handle dynamic scenes. However, these works focus on reconstruction but do not support scene editing. Some methods have also made neural radiance fields become editable in different aspects, such as editing the location, appearance, or enabling reality. But this method cannot edit the dynamics in the scene. To address these problems, we propose EditableNeRF. For an input sequence of a scene containing two moving cups, first we detect and initialize key point for each cup. Then we train our key point-based network to model the dynamic scene. This network takes a query point X as input and outputs its density and color. And key point positions will also be inputted into the network. And after training, we can edit the scene by controlling the key point positions. For key point detection, we use a reconstruction method HyperNeRF. This method uses intermediate variables called ambient dimensions, denoted as A, to model motion and topology status. When a fixed position X have different motion status, the corresponding A will have different values. So for every point X, we compute the variances of its A during the whole sequence, and select the points with significant dynamics as our initial reference key points. Specifically, we use a Gaussian filter and select the positions with the locally greatest variances as our reference key points. For our network architecture, we follow the design in NeRF, and our network takes the query point X as input and outputs its density and color, which can then be used for volumetric rendering. For each point X, we first use a warp field to deform it to a canonical position. This warp field only models some slight movements, but cannot model topological changes. We find that motions and topological changes are always related to some movements of surface points, so we use surface key points to model different topology and motion status in canonical space. And different locations in the canonical space should be affected by different key points. So for each point, we use a network called weight estimating network to decide which key point should control its dynamics. This network takes the canonical query point as input and outputs its key point weights. Then we calculate a weighted key points vector as a linear combination of all key point positions using the key point weights. And we will use the weighted key points vector to model the dynamics at X. We feed this vector and the canonical query point to a NeRF MLP, and this MLP outputs the corresponding density and color. And then we can render images using this density and color through volumetric rendering. In our network training, we optimize the key point positions in each input frame. We use optical flow and depth maps to supervise the key point positions in order to keep the time consistency of our key points. First, we propose a motion loss to ensure that the 2D key point positions in two adjacent frames are consistent with the optical flow. Then we use a geometry loss to keep the key points on the object surfaces using the depth maps. Both the optical flow and the depth maps are obtained from previous method and will also be used to track the key points for training initialization. Besides, we also use a warp regularization loss for the warp field and a reconstruction loss for the rendered images. After training, users can easily edit the dynamic scene by controlling the key point positions. Here we show more editing results of our method, including frame movements on the table and editing 3 objects individually. Here we compare our method with a NERF editing method called NERF. CoreNERF only supports one-dimensional editing and requires user annotations, while our method supports up to 3-dimensional editing without manual supervision. We also perform quantitative comparisons on a synthetic dataset, and ours reaches the best performance. Some key designs are also evaluated in our ablation studies. Our modeled scenes can also be driven by motions from other sequences. Here, the phonograph toy modeled by our method can be driven by the disc in the source video. We also implement a GUI for editing and null view synthesis. Users can use the left widget to edit the scene and use the right widget to change viewpoints. And users can also draw a trail of the key point on this GUI, and the final video can be automatically generated. That's all, thank you. Our code, dataset, and more details can be found in our project page.